The nature of warfare has evolved significantly in the 21st century, with air superiority becoming one of the most decisive factors in determining the outcome of conflicts. Nations are no longer just defending borders on land and sea. They must also secure their skies against increasingly advanced threats. Türkiye, positioned at a strategic geopolitical crossroads, faces a wide spectrum of aerial threats, ranging from traditional fighter aircraft to cutting-edge hypersonic missiles and autonomous drones. To counter these challenges, Türkiye has been developing an advanced, integrated air defense architecture commonly referred to as the Steel Dome. This steel dome is not a single physical structure, but a comprehensive, multi-layered defense network designed to detect, track, and neutralize aerial threats before they can cause damage. It combines radar systems, interceptor missiles, electronic warfare, artificial intelligence, and networked command systems into a unified shield. The scientific principles behind this system are rooted in physics, engineering, mathematics, and computer science, making it one of the most complex technological undertakings in modern defense. Today, we will talk about Steel Dome, the scientific basis of Türkiye's air defense system. So, before we start, make sure to hit the like button and subscribe to my channel. The concept of layered air defense. At the heart of Türkiye's Steel Dome lies the concept of layered defense, a foundational doctrine in modern air and missile defense architecture. This strategy ensures that threats are engaged at multiple stages and distances, significantly increasing the overall probability of successful interception while minimizing the risk of system failure. Instead of relying on a single line of defense which could be overwhelmed, bypassed, or degraded, multiple interconnected systems are deployed at different altitudes, engagement envelopes, and operational ranges to form a cohesive and adaptive shield. From a scientific and engineering perspective, layered defense is deeply rooted in probability theory, systems engineering, and risk mitigation principles. Each additional interception layer statistically decreases the likelihood that a hostile target will penetrate the defense network and reach its intended objective. Long-range systems are designed to detect and neutralize threats at high altitudes and extended distances, and often during the early or mid-course phases of flight. Meanwhile, medium and short-range systems act as successive safety nets, providing backup coverage closer to critical infrastructure, population centers, and strategic assets. This carefully structured redundancy ensures that even if one layer is compromised, saturated, or fails due to technical or operational limitations, other layers remain fully functional. The result is a resilient, flexible, and robust defense structure capable of adapting to a wide spectrum of aerial threats, including missiles, aircraft, and unmanned systems, radar systems, and electromagnetic science. Radar is one of the foundational technologies behind the Steel Dome, forming the first line of detection and situational awareness in the entire defense architecture. And it operates on the principle of electromagnetic wave propagation, where energy in the form of radio waves is transmitted into the surrounding environment. Radar systems emit these waves in controlled pulses that travel through space, interact with objects, bounce off their surfaces, and return to the receiver with valuable information about the target. The time delay between transmission and reception determines the distance to the object, while frequency shifts, explained by the Doppler effect, reveal the speed and direction of the object relative to the radar system. By continuously analyzing these returned signals, radar systems can construct a dynamic and real-time picture of the airspace. Modern Turkish radar systems utilize advanced phased array technology, which allows them to electronically steer beams at extremely high speeds without requiring any mechanical movement. This not only increases reliability by reducing wear and tear, but also enables near-instantaneous repositioning of the radar focus across different sectors. This capability enables rapid scanning of vast regions, exceptional precision in tracking, and the ability to monitor and engage multiple targets simultaneously, even in highly congested or contested environments. Additionally, these radar systems incorporate sophisticated signal processing algorithms and filtering techniques to distinguish between real threats and background noise, such as birds or atmospheric disturbances. They are also designed to operate effectively in challenging conditions, including adverse weather, terrain interference, and deliberate electronic countermeasures like jamming and deception. By integrating adaptive frequency hopping, low probability of intercept (LPI) features, and anti-jamming technologies, the system maintains high accuracy and resilience, ensuring reliable detection and tracking even against technologically advanced adversaries. Missile guidance and interception. Physics. Intercepting. A fast-moving target requires extremely precise calculations, rapid decision-making, and the application of advanced principles from physics, mathematics, and control engineering. Missile guidance systems in Türkiye's Steel Dome rely heavily on proportional navigation, a sophisticated method that continuously adjusts the interceptor's trajectory based on the predicted future position of the target rather than its current location. This predictive capability is crucial when dealing with high-speed threats such as ballistic or cruise missiles, where even a small delay in response could result in a miss. This process involves solving complex differential equations in real time, often within fractions of a second, using onboard computers and high-speed processors. The interceptor must constantly calculate where the target will be at a future point in time, taking into account variables such as velocity, acceleration, maneuverability, and environmental factors like air resistance, and adjust its flight path accordingly. Advanced guidance systems may also incorporate inertial navigation systems, INS, GPS, updates, and data links from ground-based radar to refine accuracy throughout the flight. In many cases, modern systems use hit-to-kill technology, and which relies purely on kinetic energy rather than explosive warheads. This means the interceptor physically collides with the target at extremely high speeds, often several times the speed of sound. The physics behind this is straightforward yet immensely powerful. The kinetic energy generated by such a high-speed collision, described by the equation E equals 12 mv squared, E equals 1/2 mmv squared, E equals 21 mb squared, is sufficient to completely destroy or disable the target upon impact. Additionally, this approach minimizes the risk of unintended explosions and reduces collateral damage, making it especially effective in defending populated or sensitive areas. The precision required for hit-to-kill interception also drives continuous advancements in sensor accuracy, guidance algorithms, and propulsion systems, ensuring that interceptors can perform reliably even against evasive or maneuvering targets in highly dynamic combat environments. Infrared and electro-optical detection. While radar is highly effective, it is not foolproof. Stealth technologies can reduce radar visibility, making it necessary to use additional detection methods. Infrared, IR, and electro-optical sensors provide this capability. These systems detect heat signatures emitted by engines or high-speed friction. Based on thermal radiation laws, they can identify objects even when radar signals are weak or absent. By combining radar and IR data, a process known as sensor fusion, the steel dome creates a more comprehensive and accurate picture of the airspace. An electronic warfare and signal disruption. Electronic warfare, EW, is another critical component of Turkey's air defense strategy. Instead of physically destroying threats, EW systems disrupt or disable them by manipulating the electromagnetic spectrum. This includes radar jamming, GPS spoofing, and communication interference. The science behind EW involves signal processing and electromagnetic theory. By overwhelming an enemy's sensors or feeding them false information, the system can neutralize threats without direct engagement. This capability is particularly valuable against advanced missile systems and drones that rely heavily on electronic guidance. Artificial intelligence and automation. The complexity of modern air defense systems requires rapid decision-making, often beyond human capabilities. The artificial intelligence, AI, and machine learning play a crucial role in managing this complexity. AI systems analyze vast amounts of data from sensors, identify patterns, and classify threats in real time. They can prioritize targets based on risk and recommend optimal responses. These capabilities are based on statistical modeling, neural networks, and optimization algorithms. By reducing human reaction time and improving accuracy, AI significantly enhances the effectiveness of the steel dome. Network-centric warfare and communication systems. The steel dome is not just a collection of independent systems, it is a fully integrated network. Radar stations, command centers, and interceptor units are connected through secure communication links. This network-centric approach allows for real-time data sharing and coordinated responses. The underlying science is based on information theory, which governs how data is transmitted, processed, and stored. Advanced encryption ensures that communication remains secure, even in the face of cyber threats. This interconnected structure allows the system to function as a unified whole, rather than isolated components. Domestic defense industry and engineering excellence. Turkey's investment in its domestic defense industry has been instrumental in the development of the steel dome. Indigenous systems such as HISAR and SIPR are designed and produced locally, reducing dependence on foreign technology. These systems incorporate advanced engineering principles including aerodynamics, propulsion, and materials science. Interceptor missiles must withstand extreme conditions, including high temperatures and pressures during flight. This requires the use of specialized materials and precise engineering to ensure reliability and performance. Challenges of hypersonic threats. One of the most significant challenges facing modern air defense systems is the emergence of hypersonic weapons. These missiles travel at speeds exceeding Mach 5, making them extremely difficult to detect and intercept. The physics of hypersonic flight involves complex phenomena such as shock waves and plasma formation, which can interfere with radar detection. To counter these threats, the steel dome must incorporate advanced tracking algorithms and high-speed interceptors. Ongoing research in this area is critical to maintaining effective defense capabilities. Ballistic missile defense mechanics. Ballistic missiles follow a predictable trajectory divided into boost, mid-course, and terminal phases. Each phase presents different interception opportunities. Mid-course interception occurs outside the Earth's atmosphere and relies on long-range systems and space-based sensors. Terminal interception happens as the missile re-enters the atmosphere and requires rapid response systems. The science behind these operations includes orbital mechanics, atmospheric physics, and high-speed guidance systems. Countering UAV and drone threats, unmanned aerial vehicles, UAVs, present unique challenges due to their small size, low altitude, and ability to operate in swarms. Traditional air defense systems are not always effective against these targets. To address this, but the Steel Dome incorporates specialized counter-UAV technologies, including radar, radio frequency detection, and directed energy weapons such as lasers. Laser systems operate by focusing electromagnetic energy onto a target, causing damage or destruction. This approach is both precise and cost-effective, making it ideal for countering large numbers of drones. Environmental and geographical considerations. Turkey's diverse terrain adds another layer of complexity to air defense planning. Mountains, coastlines, and urban environments can affect radar performance and system deployment. Engineers must account for factors such as terrain masking and atmospheric conditions when designing and positioning systems. This ensures optimal coverage and effectiveness across different regions. A system reliability and redundancy. Reliability is a critical requirement for any defense system, especially one as complex and mission-critical as the Steel Dome. In high-threat environments, even a minor system failure can have significant consequences, which is why the architecture is designed with multiple layers of redundancy to ensure continuous and uninterrupted operation. The goal is not just performance under ideal conditions, but consistent functionality under stress, damage, or electronic attack. This includes backup power systems to maintain operation during outages or attacks on infrastructure, duplicate sensors that can take over instantly if primary units fail, and alternative communication links to prevent loss of coordination between different components of the network. These redundancies are carefully engineered so that failures in one subsystem do not cascade into larger system-wide disruptions, a concept known as fault tolerance. Reliability engineering plays a central role in achieving this robustness. It uses statistical models, failure rate analysis, and predictive maintenance techniques to anticipate potential points of breakdown before they occur. Engineers simulate extreme scenarios, such as high-intensity attacks, harsh environmental conditions, and electronic warfare interference, to test system resilience. Components are often designed with high mean time between failures, MTBF, and are subjected to rigorous stress testing to ensure durability. Economic and technological impact. The development of the Steel Dome has significant economic and technological implications, and it requires substantial investment in research, development, and manufacturing. However, it also drives innovation in fields such as electronics, aerospace, and software engineering. These advancements can have broader applications, contributing to economic growth and technological progress. Future innovations and advancements. The future of Turkey's Steel Dome will likely involve the integration of space-based sensors, quantum communication, and more advanced AI systems. Space-based assets can provide early warning of missile launches, while quantum technologies could enhance communication security. These innovations will continue to push the boundaries of air defense capabilities. Turkey's Steel Dome represents a sophisticated and comprehensive approach to air defense, combining multiple scientific disciplines into a unified system. Its layered architecture, advanced detection technologies, and network-centric design make it a powerful tool for protecting national airspace. As threats continue to evolve, so too will the technologies behind systems like the Steel Dome. Through continued innovation and investment, Türkiye is positioning itself at the forefront of modern air defense. If you liked this video and would like to see more like it, please give it the thumbs up, leave a comment, and click the button to subscribe.